Well, welcome to the Minnesota Stormwater series. My name is John Gulliver. I'll be introducing our speaker and talking a little bit about where the Minnesota Stormwater series came from. It was funded by the Minnesota Legacy Amendment, which gave money to the Clean Water Council, who gave money to the Minnesota Water Resources Center, who asked us to put on this seminar series. The idea is to bring in people from around the country who have an expertise to talk about stormwater. Today we're going to talk about modernizing performance metrics. We'll have a talk by our invited speaker and then a panel discussion. So it's my pleasure to introduce Elizabeth Fassman-Beck. Elizabeth is an associate professor at the Stevens Institute of Technology. She has worked for 15 years in stormwater research in New Zealand and the United States. So that gives her an international perspective. She received a PhD in 2002 from the University of Virginia, and she is known as being, I think, the only person to have given a TED Talk on green infrastructure. She also has started a living laboratory for green infrastructure at Stevens Institute. It has 38 green roofs systems. These are pilot scale systems. 4 other planter box systems, bioretention planter boxes, and 3 bioretention systems. So it's something, it's a lot of work to start a laboratory on your own, and Elizabeth has the energy to do that. So please join me in welcoming Elizabeth Fassman-Beck.
Thank you. Thank you, John. Thank you, Andy. Thank you to all here at the University of Minnesota. It's really exciting to be here, and I feel like I'm in pretty impressive company with the speakers that have come before me in this seminar series. I'm pretty honored to be part of this whole thing. I will say one sort of correct one thing about the TED Talk. Marcus Quigley gave a TEDx as well, not specifically on green infrastructure, but he falls into our circle of friends, I'd say. So that was pretty cool. So thank you again for coming. Hopefully I am caffeinated. Hopefully you are caffeinated and ready to think about performance metrics on a Monday morning. So Stevens Institute of Technology, for those who are not familiar, is in the foreground of this picture. We are a small technology-focused university on the banks of the Hudson River. I'm pretty sure everybody's familiar with the view in the background. That, I say we have the best view of any college campus in America. It's pretty cool, but that said, I'm also transitioning from Stevens after all this effort of building the living lab, which we'll talk about some of the systems in a couple of minutes. But after all this energy of building the lab, I've kind of been offered the chance of a lifetime in Southern California. And so just over the next couple of weeks, I'm actually moving to Southern California to join the Southern California Coastal Water Research Project, otherwise known as SQUIRP, to continue in an applied research career, helping with Southern California's stormwater problems. So doing all the same research, all the same kinds of research, but instead of now a very humid and wet East Coast, I'm going to an arid, dry, Southern California, where it doesn't actually rain, but apparently they have really big stormwater problems and need an engineer to help. Who am I to say no? You know, that sounds pretty cool. Okay, so here we go. My career has been focused on performance monitoring of stormwater BMPs. I've progressed from basins to constructed wetlands to floating treatment wetlands, which kind of combine the technologies of wetlands and basins. From grass swales to bioswales, then to permeable pavements at the street level, up to green roofs on the rooftop, and looking at bioretention systems at multiple scales, full-scale systems, and these small size really urban environment planter systems. And just for the record, because we're in Minnesota, it snows in New Jersey, so I've been looking at cold weather too. I chose this picture of a very unhappy looking rain garden because I get what you guys are looking at too. Okay, sorry, I'm already digressing. All right, but it's been about 40 years of stormwater. It's been about 40 years since the NPDES permits came online, and 30 to 40 years of stormwater research. And we've changed the technologies. We as researchers have tried to improve the technologies, but ultimately, even after about 30 to 40 years of stormwater management, the metrics that we use to assess performance and the permitting objectives, the policy aspects of it, have largely remained unchanged. So I think it's a fair question to ask, if we've been developing these technologies and understanding them better, and we can design them better, but they're still being built to old standards, it seems this is a conundrum, and to me, this is possibly the biggest impediment to actually protecting downstream environments. In my opinion, it's a really important question to consider, these performance metrics, because regulatory services and policymakers tend to be the ones who issue the design guidance. So, or we could think about it as policy drives BMP design. The policy folks are usually the ones who are issuing the design guidance and setting minimum standards. And let's face it, the vast majority of designs that are submitted or that get built are built to minimum standards. So there's a very strong link between policy and design. I think about this, these links at 3 scales. Broadly speaking, so we're speaking very broadly here. Some jurisdictions, and you guys are one of them, have some more forward-thinking objectives, but we're talking at the broad scale here. So to site scale, you've probably got a design engineer who's primarily concerned with an NPDES permit. Those permit conditions are usually some arbitrary set of flow controls and maybe an 80% TSS reduction. And they're probably, and then the design approach is probably based on a rule of thumb and some percent removal, maybe TSS, maybe some nutrients, but that's all that they're trying to do is meet those permit conditions. At the watershed or sewer shed scale, we're really policy driven, trying to meet TMDLs, which I know are apply around here. You've got some TMDLs that you're working towards. In the Northeast, there's a lot of CSO mitigation. And broader in the Great Lakes area, there's a lot of CSO mitigation strategies that are designed at a watershed or sewer shed scale, but again, driven by a policy objective. But ultimately, what we're really trying to do when it comes down to it is protect or restore a downstream environment. We're trying to protect and restore beneficial uses or ecosystem services. And whatever we do on these scales is ultimately supposed to have an effect over here. But the question is, with our design objectives, and I'm going to focus really at the site scale today, do the design objectives that we have here and the metrics for designing and building and assessing performance really have any meaning when we get down here? So as an example of a typical site level stormwater control measure or best management practice, what's the term that you guys used here? Best management practice? Okay, so we'll go with BMP. Right, let's just add the acronym thing on top of everything. So feel free to shout out if I'm using an acronym that does not apply here, and I'll translate. Right, that's my international experience. I can translate stormwater acronyms all over. Now I'm learning a whole new set for California. Wow. Okay, and I should have said, I also like to keep things a little bit informal. So if you do have questions along the way, shout out. For those online, I will try to repeat the question so you hear it. Yes, look at that.
What is CSO?
Oh, combined sewer overflow. CSO is a combined sewer overflow. So you have a mixture of stormwater and wastewater, discharges untreated into a receiving environment, pushing all that untreated sewage into the receiving water. So big deal for Milwaukee, for Columbus, for not so much for Twin Cities, but elsewhere in your region, it's definitely an issue. Okay, so we're talking about what I'm gonna call an outdated design objective. So do you guys have a flow control objective to reduce a 2-year peak flow to, in post-development to a pre-development condition? Probably the 2-year peak flow in pre-development or some variation thereof, right? This is everywhere. And this is supposedly to protect the receiving water from stream erosion. Here we've got some pretty significant stream erosion. Those are outfalls right there. And this is an urban creek. So the objective is to minimize stream erosion by reducing the 2-year, say 24-hour storm to a pre-development level. Does anybody know where that comes from? I think John does, by the way he's smiling. Does anyone know where this comes from? Research, yes, in 1964 on natural streams. Yeah, so this research that was led by Leopold and his group on natural streams identified that that bankful flows were important in stream geomorphology for shaping the stream channel, and bankful conditions typically occurred in natural streams from a 2-year flow, a 2-year return period flow, not storm, but flow. So in the absence of anything else, this idea found its way into stormwater management to protect streams from erosion. We have ubiquitous across the US, in New Zealand as well, probably elsewhere. There's some variation on controlling the flow, the maximum flow from 2-year storms. I'm pretty sure that our urban streams are not really natural streams. And a 2-year flow condition is not going to have much of an erosion impact on a concrete armored channel. And even here, now these urban streams are in California, but even this one that looks somewhat more natural, you guys might have streams that look like this. This one is still a very highly modified system. This low flow dam actually creates an embankment to promote groundwater recharge on the upstream side. So this is a highly modified environment. Yes, there are ecosystem services. Yes, there are beneficial uses for these streams, but I'm pretty sure erosion, a 2-year stream flow is not going to be the driving factor of beneficial uses in these environments. You know, so 1964, there's been a lot of research since then, but even as far back as, and I say as far back as 1996, because now 1996 actually feels like a long time ago. In 1996, State of Maryland came up with this awesome graph. I love graphs. I hope you love graphs too, because I have a lot of graphs to show you. Even on a Monday morning, I love graphs. So 1996, State of Maryland comes up with this assessment, which says that flow impacts and water quality impacts occur over a spectrum of rainfall conditions. Our metrics, our design points right now are 2-year flow control, 10-year flow control, 100-year flow control, for good reasons. I'm not questioning the motivation. I'm just questioning, is that design point the right point? And really, we should be looking at, Maryland's suggesting here that we should be looking over a spectrum of events. Okay, so my objective today then is to just plant some seeds for alternative metrics for BMP design. For also alternative metrics, not just for design, but for how we consider performance, what kind of performance we're considering. And to me, this goes hand in hand, thinking about these BMPs differently, what they're doing and how we design them and what they could do and what we could design them for, goes hand in hand with updating or modernizing our policy and permitting, because they're the ones who hold the design manuals. And you know, all of this is chasing after that holy grail of having an impact on the downstream environment. I think that we have enough information now, or at least the beginnings of enough information, to really start thinking about how to approach design from a different set of performance metrics that actually could be related to the downstream environment. So I want to give you a couple of examples. I'm going to rely on mostly on my own data. This is not a metadata analysis. I do not have all the answers. I want to start a conversation and show you, and hopefully drop a few little tidbits in there to get you thinking. So the kind of examples I want to look at are an evidence-derived design of a new green infrastructure LID technology and applied. And basically, this is how we developed green roof technology in New Zealand to do something different. And also a couple of different ways of looking at data that we already have, and in a different way. And I've written it up here as not so new tools for data analysis. So these are performance metrics or ways of assessing performance that we all know because we learned about them in hydrology or somewhere else along the way, but we're not really applying them to stormwater just yet. But I think we have information that we can do that. Okay, so I'm gonna start with green roofs, partly because I've spent a lot of time thinking about green roofs and working on green roof design, but also because green roofs, I think, are a BMP technology that have always been subject to more scrutiny and more misperceptions than other kinds of technologies. And they're not being used that often, partly because they're not necessarily in the design manuals, and that's partly because the regulators don't understand how they work, or they might think they understand how they work and don't believe it. And then designers aren't choosing them because they're not being credited in a way that helps the site owner. So we've got this little conundrum of when it comes down to it, an engineered green roof is really only a few inches of media. So how effective could it really be, right? How effective could it be for 2-year and 10-year ongoing flow controls? And if it's so shallow and it fills up with water, if you have a really rainy period, it's not going to keep working, right? We've got all these misperceptions or all these preconceived ideas about how this technology works that I think are hindering how we think about this practice. So fortunately for me, my research on this technology was initiated at the request, well, not exactly on the request. There was a strong suggestion on my part to the regulatory agency to look into these systems. And so really, we were able to approach green roofs with an open mind and no preconceived notions. The objective from the regulatory agency was, well, you know, we're really interested, figure out how to design and build it and figure out what it should do. Because right now our manual just says it's a curve number of 61. And I'm pretty sure that's not how it actually works. So we really had a wide open purview. So here I believe you use the term green roof. In Portland, it's an eco roof. In New Zealand, we adopted the term living roof because it is a living system and that's integral to the performance. So I'm just gonna go back and forth with all these different terms. Okay, so this is, you know, breaking lots of rules on this slide, like way too many things, but this is what we did, right? We did not way too many, we did all sorts of cool stuff to figure out what materials to use, how to test them, what metrics to even use to assess performance, because we know this isn't gonna work like a pond, right? So how do you even judge whether it's working or not? How do you test the materials, the whole gamut from a true R&D perspective. And I wanna point out, this is my research partner, Dr. Robin Simcock from Land Care Research. Robin does not like to have her picture taken. So these are the kind of pictures that you get to share of Robin. But she's a soil and plant scientist. And to me, I think this was the key to figuring out how to understand how this system works. Because of Robin's expertise, I learned to think like a plant. And that's a totally different way of approaching design, but kind of critical if you're working with a planted system. Okay, so I mentioned, so this story is about what do you even think about with performance? How do you measure it, and what does it mean? So, oh, and I forgot to mention, so at the time that we started, so there, at the time and still now, there's a testing, a guide, so the only information that was out there on green roof design was from a German working group, a technical working group called the FLL, which is a word this long, and I'm not going to try to pronounce it, who have developed the guideline for planning, execution, and upkeep of green roof sites. This was the only manual out there that talked about how to test and interpret green roof results. But it's very rigid, and it gives you testing procedures, and this number should be this number should be this. No explanations of why. Sounds much like our cookbook recipes from many of our design manuals now. Several of the procedures have now been adopted or adapted into ASTM standards, but at the time that we started, there was only the FLL and no explanation for the who, what, why, when, or how. As we went into this, we had a lot of questions about not just the procedures, but the interpretation of the data that comes out of the testing regime and what that would mean for performance, and does testing in a lab have any impact whatsoever, or is it at all related to what you get under field conditions? So real questions about the design procedure, the tests that you have to do for the materials, and was it going to influence, was it going to predict a field behavior at all? So a little story about thinking like a plant and how we translate that into an engineering context. What are the parallels for engineering? So we have to look at moisture storage in porous media. I am still a professor for another couple of weeks. Okay, so let's think about how we define moisture content. We need to think about three, or actually it's gonna be 4 states of moisture content in porous media. And I'm talking about any engineered media filled green infrastructure system that has no exfiltration. So a lined bioretention cell, a concrete lined bioretention planter, a lined permeable pavement, and a green roof system. We're not exfiltrating to the surrounding soils, so it's really important to understand the moisture dynamics within the system in order to predict how well it's going to work, to design for a flow control objective. Okay, so if our moisture content equals the porosity, if our moisture content, that means that all the pore spaces, so here's our soil particle, our soil parcel, all the pore space is filled with water, that's the blue, and then you've got these little soil particles. And we measure the moisture content, this is saturation, we measure the moisture content as equal to the porosity. If our system has filled up with water, with runoff in our case, the runoff stops and there's no exfiltration, but we have an underdrain, so water discharges out of the underdrain. When that drainage stops, we are at a moisture content that's referred to as field capacity. So when we're at a moisture content equal to the field capacity, now we have still some water in there, but some of the pore space is filled with air. So we have a mixture of air, water, and soil particles. There's no more gravity outflow, but our soil is still wet. The difference in this moisture content and this moisture content is equivalent to the temporary storage and maybe stormwater detention, right? That's what we can temporarily store that's going to drain out. That's the difference between those states. So now gravity flow has ceased. The only way out for water is through evapotranspiration, right? And the plants can only access so much of the water. They can't get it all. The plant roots can only pull, they can pull a lot of water, but not all of it. And so the media dries down to the wilting point. So the wilting point is another measure of moisture content. Now there's just a little bit of moisture there, but it's still measurable. And this is gonna be the driest condition that we can achieve naturally through natural processes. And so the difference in the moisture contents between field capacity and the wilting point is then going to give us an amount of water that in theory is equal to the maximum amount of retention that we're ever going to get from the system, just counting on the media itself. So our retention or volume control is the difference between field capacity and the wilting point. And in plant science, you call that plant available water, the quantity of water. Now, that's the way soil science and plant scientists think about moisture dynamics. You've got these three states and these natural processes. Well, an engineer measures moisture content by sticking a sample in an oven. And so we take our sample that's at field capacity, we put it in an oven and we dry it to oven dry, and we get a measure of moisture content. So I would call this a geotechnical engineering approach to measuring moisture content. It's also the method that's in that German testing procedure, the FLL, and also now in the ASTM standard. So what we were trying to do, back to our story in Auckland, what we were trying to do was design a media that maximizes stormwater capture. And in the process, we wanted to figure out how to create some specifications for what that should be, how you should measure it. So that's going to give us some indication of our stormwater capture, actual measure of stormwater capture. Okay, so an engineered substrate, is everybody cool with engineered substrates? You've got a mixture of potentially natural or man-made materials with some organic content, some minor fraction of organic content to help the plants grow. But the bottom line is, the key thing about an engineered growing medium is that we can manipulate the characteristics of that system to manipulate field capacity and wilting point. And we can design it to maximize the difference between these two because we're engineering the substrate. So science meets engineering. So over time, in Auckland, we designed a lot of substrates and built a whole bunch of green roofs and monitored them. So our main systems, we wound up with, these are just the names of the 3 different sites. We wound up with varying design combinations of materials and depth of green roof. So, and measured them for, in some cases, 6 months, in other cases, over 2 years. Okay, so here's the question. How do we assess the materials in the lab to have some effect on real life, or to have some prediction for real life? And then how do we manipulate those materials to maximize that benefit? So we extracted from all this data that we collected, we looked at 3 different ways of measuring moisture holding, right? So the blue diamonds are that plant available water, how the plants think, or how the plants in the soils actually behave for that difference between field capacity and wilting point. There's another, and that's measured using a horticultural technique in the lab, or agronomic methods in the lab. There's another step to that where we can add a little more water, effectively add a little more water, but it's another agronomic or horticultural interpretation. That's plant available water with something called stress water. The details don't really matter, but it's another ag measure. And then we compared it to the prediction that we'd get from the geotechnical test. So the bottom line is, we have 3 different ways, 3 proposed methods for measuring in the lab stormwater retention in the field. That's what we're trying to assess here. 3 different test methods. Do any of them have any impact or relation to what's actually happening when it rains? So it turns out, long story short, this graph doesn't look like much, and there are big error bars. But this is actually hundreds of data points in here. 5 different substrates, multiple depths, and had to condense the data to be able to see it. So like that data point is actually the average of 10 events, plus the bars are showing the range. In there, that one has 12 events behind it. Over here, there's 60 events behind this one little data point, somewhere right in here, I think. Right now, you're supposed to say, whoa, that's a lot of data. There's a lot of evidence supporting this. And what it boiled down to, on average, the maximum event retention that we actually measured in the field was statistically not different than our lab measure of plant available water. So this, all of a sudden it's like, oh, well, those plant scientists might be onto something, right? But as an engineer, I can manipulate that factor of plant available water in the design of my system. And I'm not picking on the plant scientist. I mean, she's changed the way I look at everything. So this is really all in honor, in awe. So anyway, this kind of, this paper and this discovery led us to win the 2014 ASC Horner Award moving forward. And so why is this important? What can we do with this? Oh, sorry, skipping to the punchline. So this is great, but now I'm telling everybody, you know, you need to think like a soil scientist. We need to do different tests. We need to learn different methodologies and different ways of thinking about things. And really the geotechnical test is much easier to do. Stick it in an oven and a few hours, you're done. The agronomic test takes days. It's just it's not labor intensive, it's time intensive. You set it up and you just let it go. So the geotechnical test is easier to do. What happens if you use the geotechnical test instead of our plant available water? Well, in our substrates in Auckland, it turns out you make a big mistake. And with the substrates that we developed in Auckland, using that geotechnical test or the FLL testing procedure almost doubled the estimate of stormwater retention. That's going to be a big oops in terms of interpreting then, is this system going to protect a downstream environment if we're actually predicting double the capture that we might achieve. In this case, I should also say that in this case, I think the reason that this difference is so significant, our substrates primarily rely on pumice as the aggregate. Pumice is the coolest rock ever because it holds water in its pores. And so that has a real advantage when you're talking about stormwater capture. If you were using expanded clay or expanded shale or some of the other expanded man-made materials, I'm not sure that the difference would be quite as strong, but I don't have that data to show. But that's a hypothesis. Okay, so, but how do we turn this into design? Well, now I can say, okay, I've got a design storm that I need to retain. I want to retain a 1-inch storm, or New Jersey, a water quality storm is 1.2 inches. I think in North Carolina as well. I want to fully capture a 1.2-inch storm using a green roof. Well, I take my design storm depth and I divide it by the plant available water when it's measured as a fraction. And I get the depth of a living roof. The depth of media, sorry, I use the term living roof, and I didn't do a good job of defining my variables on this slide. The depth of media that I need to fully capture that design storm comes out of that calculation. And so here I've just plotted up this relationship that we can then use for design, but also to manipulate the materials. So a higher organic content material is going to tend to have a higher plant available water, but you get out here and with this high of organic matter and you're going to wind up with other design issues like it doesn't drain well. Whereas at the low end of the spectrum, you get a really sandy material that probably doesn't hold enough water to support your plant life. So somewhere in here is a sweet spot, but you've got this range that you can manipulate and an opportunity. Okay, so, oops, sorry. I had the same problem when I was doing the TED Talk. Actually, well, it wasn't me, it was the clicker. And in that case, brain break for a second. Just think about all that while I tell you another story. So I'm standing facing the audience. I have no view of the screen whatsoever. And I can't look back because you're doing a TED Talk. And the clicker, every time I pressed it, would skip forward like 10 slides. And the audience was kind of looking at me like I was crazy. And I finally, and someone, my department chair, goes like this. And I turn around. Anyway, after that, they knew to tell me every time. Okay, refocus, a little bit of a laugh, something. Right, all right. So here I've been designing for a 1 to 1.2 inch storm. That's great, but what do I do about that 2-year event? Because I still have to meet that 2-year event for my permitting. Yes.
How did you optimize for unit weight? Half weight, get twice the depth.
Okay, Good question. So the question is, how did I optimize for weight? Because with half the weight, I could get twice the depth. So it turns out, that's a good question. It turns out that this relationship is only good up to about 1.2 inches. Empirically, with data, not only my own data, now I've looked at data from a lot of different places. People are really happy to share their green roof data. And empirically, it seems like there is a maximum capture from a green roof system that hovers right around the 1 to 1.2 inch depth when we're relying on just the media alone. There are a lot of other design criteria for the media for safety. So number one is the weight, and that relates back to ponding. So in a green roof system, you do not allow any ponding on your rooftop, and that's for safety. So what that translates into is a very coarse, a really coarse media. It doesn't look like a bioretention media. It looks more like a pile of rocks. So because you have, and because it's very coarse, you don't have a lot of capillary action. So at some point, doubling media depth does not give you a double capture. And it seems like so far, with the evidence that we have, with the data that's out there, that maximum capture depth is right around 1 to 1.2 inches. That answer your question? Yeah, great. Okay, so how about in the context of our 2-year event, because we've still got to now go from our site scale to our receiving system impacts, and a 1 to 1.2 inch event is definitely not a 2-year event. In New Jersey, a 2-year event is about 3.5 inches. So how does this fit into that spectrum? Well, instead of just crossing the technology off the list because it might not meet that 2-year flow, what else can we look at that it does that could be really beneficial for protecting those downstream environments? So for us, in this case with green roofs, some researchers in Norway have presented us with another way of looking at the data, and they're using flow duration curves. So how many people have taken hydrology? How many people remember flow duration analysis? And what's it used for? Downstream assessments, receiving stream, habitat quality, maintaining minimum environmental flows. That's often a lot of what it is. Probably around here, flow duration is used more for power supply. I just realized maybe, no? Okay, never mind. We'll go with the downstream flow ecology, go back to that. So this is a tool we know, but we're not using. So these are a couple of flow duration curves developed from monitoring data from a couple of roofs in 2 cities in Oslo and Trondheim, 2 cities in Norway. And I'm borrowing this data because I was really fortunate to host the PhD student who did this work. So I worked with her, or she came and worked with us at Stevens for 4 months. And through the process of our discussion, we came up with, she could look at her data using this flow duration analysis. So what does it do? A flow duration analysis gives us or demonstrates compliance or exceedance with an allowable discharge rate under all conditions. Right? For example, in Oslo, I'm going to say it wrong. One of these cities, hang on. Okay. In Oslo, there is a known sewer capacity. Imagine that, you actually know the capacity of their sewers. That's awesome. I wish I could say that for every city. So there is an allowable discharge rate from a developed site of 10 liters per second per hectare of your site in order to maintain capacity in the downstream sewer. And the flow duration analysis says that an undeveloped or a developed uncontrolled site exceeds that flow threshold for 34 hours. But where there are green roofs installed, we only exceed that threshold for 13 to 16 hours. So now you've cut exceeding your capacity in the downstream environment by half. It's not the whole solution, but that is a measurable effect. In Trondheim, where there are combined sewers, the duration of an uncontrolled combined sewer overflow contributing to it would be 50 hours. But with our green roofs installed, there's some speculation here because we're talking about network-wide versus site-wide analysis, but it gets us thinking about how to use these tools. We go from a 50 hours of exceeding the capacity down to 4 to 8 hours. That's a massive effect. Does the 2-year flow control point have anything to do with it? Not at all. So just a different way using tools that we already have of looking at actual downstream effects. Okay, if flow duration analysis is too hard, and sometimes I think it's too hard, we can look at just a frequency analysis of your peak flows. So this was from my permeable pavement monitoring in Auckland. I have the same graph for all my green roof sites, but I just wanted to throw another technology in there for fun. Looking at the occurrence, it's just the occurrence of peak flows of certain magnitudes. So our black line is the uncontrolled asphalt catchment peak flow, and the dashed line is pre-development that's been modeled, and the gray line is from the underdrain. Did I get that right? The dashed line is the underdrain, the gray line is the modeled pre-development runoff. So just the occurrences of peak flows are happening nearly on the same spectrum as our pre-development condition. That's pretty cool, and that analysis is really easy to do. We can also see that our 2-year, 10-year, and 100-year storms are pretty close to our pre-development conditions. And that's looking over a spectrum of events, not just this one day that it rained with this intensity. I hope I said that right, because now I'm sort of rushing through. All right, I want to talk just for 2 minutes about water quality, hopefully 2 minutes. And gonna go back to green roofs. Again, I think about green roofs a lot. I do a lot of work with green roofs. Okay, so our typical water quality objectives for the metrics that we're using for assessing whether a BMP meets a water quality objective is usually an 80% TSS reduction, right? Is that what's your objective here? Around there, okay. So somewhere between a 70 and 85% TSS reduction, maybe some percent reduction of total nitrogen and total phosphorus or total phosphorus. Really, what I suggest that we should be considering is the nutrient forms that are actually contributing to eutrophication downstream. It's not total nitrogen and total phosphorus. Inorganic nitrogen and orthophosphate are the forms of nutrient that plants can uptake. We should also be looking at effluent quality and not just a percent reduction. I feel obliged to say that, but I'm not going to go into detail on that one. I'm going to talk about the nutrient forms for a second. Okay, so magic number. Here's another good little history lesson. Where does 80% TSS removal come from? And why is it across the country the objective? I've cheated, and the answer is on the slide. I didn't do my animations right. So this magic number of 80% TSS removal came from 1993 CZARA, Coastal Zone Reauthorization Amendment Act, or something like that. And it got, again, in the absence of any other information, to protect coastal zones and coastal zone quality, they, within that purview, came up with an 80% reduction, and that made its way into NPDES permitting and remains to this day. Through the NERP program in 1983, we also found out that there's a lot of other stuff in stormwater, but we know how to do sedimentation. We've got all these basins that are out there for flood control. Let's just enhance the sedimentation, and we're gonna hope that we remove other pollutants by default. But really, this is what we're trying to avoid, right? Here's a detention basin. Yes, there are nutrients in there. You can tell by that algal bloom, right? So I'm not really sure this is the right tool for the job, nor is assessing total phosphorus or total nitrogen. So I already talked about those. We have other forms that are the ones that contribute to eutrophication. So if, going back to my green roof data, sorry, I just shouted in the mic to those listening online. If I were, here's some data, this is work in progress from what we're doing right now with green roof water quality. The reference roof total phosphorus is down here. That's the box plot, okay? Here is the range of total phosphorus that we're measuring off of green roofs. So I'm kind of picking on green roofs here, but I love green roofs. We're gonna get there. There's a solution. If we're looking at total phosphorus, we're missing a big part of the picture. If we're designing for total phosphorus removal and sedimentation and particulate matter, it turns out that 91 to 95% of all the phosphorus in the green roof discharge is orthophosphate. It's dissolved. And if I'm designing for sedimentation, I'm not going to affect the problem, or I'm not going to create a solution for this problem. So, as I said, I love green roofs. I love green roofs everywhere, including my dad's HO scale train set. You know, and again, green roofs receive a lot of attention for different reasons. So I'm not trying to pick on this technology, but again, it's a technology that's under more scrutiny than most. And the concerns about nutrient discharge seems to be a bit loud. And we're picking up on that same conversation for bioretention, right? How do we design our media so that we have a sink for pollutants and not a source? Okay, so here's our problem. We've got, looking at event mean concentrations of nitrogen and phosphorus, there's more nutrients in the discharge from the green roof than the reference roofs. We have two choices for designing a solution to this, or rethinking how we design the system. We could increase retention. We can go back to manipulating the properties of the media, but that's still not, that's not addressing the whole problem, right? Our other, because when we look at the mass discharge, so when we incorporate that retention aspect, yep, we're having an effect. It's going in the right direction, but we haven't totally solved the problem. We need to work on decreasing that concentration. We cannot rely on the flow control or the volume control alone. So here's our 38 pilot scale green roofs at Stevens Institute of Technology, where we're systematically changing the materials that are used in the media to address nutrient control and capturing water quality samples. Sorry, go really quickly through the end of this. The innovation for a solution. So we're looking at the materials in the green roof, but we're also looking at innovating a solution with including what we call a downstream permeable reactive barrier. It's just a strip of another material at the downstream end that hopefully preferentially captures up these nutrients. This PRB material, we're currently testing 3 different materials for all of our substrate combinations. But you could retrofit this onto an existing roof because it's a downstream control. And we seem to be getting somewhere, right? So here's our, we're affecting that concentration, and that's affecting the mass as well. So by looking at the right form of pollutant, we're able to create the right solutions to protect that downstream environment. So where does this get us to? I don't have all the answers, but I think we have a lot of tools and a lot of data available to us to start thinking about technologies in different ways and solving different problems that we have evidence now that we can relate to a receiving environment effect. And I put friendly scientists on here because working with scientists has changed my whole perspective on everything. We know Professor Gulliver and I were talking just before the seminar started, and as an engineer, I feel like I have enough science to kind of be dangerous, right? I have enough science to create a solution, but I really need to go back to those scientists and I need their input to say, well, what actually happens downstream? What's the design point? What are the design points I need to protect that downstream ecology or the ecosystem services? And I can back that up into a BMP design that's actually meaningful. And a last little thought from a bathroom stall in Newark Penn Station, which is not usually my go-to place for inspiration. But this was a little gem. If you change the way you look at things, the things you look at change. And I think we need to broaden our perspectives, not only as designers, but we really need to be working with those policymakers because they write the rules. And with that, I'll say thank you. And despite heading to California, I fully intend to keep operating the Living Laboratory. There's a whole lot more going on that I didn't get to share with you because I could talk for hours. And this doesn't happen without lots and lots of help from undergrad students, from graduate students, some volunteer help from the US EPA, from software engineering, because we've got so many instruments going on there. I couldn't possibly manage all that data by myself. So wow, the power of software to make my life easier is amazing if you're talking to people that know how to do it. And lots of support from facilities management at Stevens who've helped me build all this and make this happen. And undergraduate research programs, support programs at Stevens, helping bring in the bodies that are needed to make all this happen. And some funding support from Washington, D.C. Department of Energy and Environment. That's not specifically on the green roof water quality, but that funding is ending, and we really want to continue. We've got 3 years worth of data, and that is just the tip of the iceberg. Anyway, with that, I will say thank you, and hopefully have time to answer a few questions if there are some.
Elizabeth. Thank you. Thank you. So questions for Dr. Liz? Yes. I asked you.
Thank you. Our manual and our MIDS calculator, which is a widely used tool here in Minnesota, give the volume credit the way you described it, evapotranspiration and so forth. We give 0 credit for phosphorus. Can you talk a little bit more about the materials that you are using for the reactive membrane? And has there been any discussion of the possibility of using plants that have a lower nutrient need?
Okay. When you said they give 0 credit for phosphorus, is that for a green roof specifically? Okay. So the plants, I'll start with the plants because that one's a little bit easier. The plants that we're using in the majority in 30, in 26 of the systems are just a variety of sedum blends. So my expertise, I'm not the plant person. So I went to Emery Knoll Farms, and who is a specialty green roof plant supplier, and said, I'm building these green roofs. What would the industry use in our region? So the plants are the same in the vast majority of my experiments, and they are low demand sedum varieties that are chosen for the Northeast. So I kind of already have that one ticked off, although the other 8 tables that we have are actually planted with crops, so herbs and salad greens. And that's where the Washington DC's question came from, is if you have a crop producing green roof, is it different water quality than a stormwater green roof? And those are heavy nutrient demand crops, and we're seeing a lot more nutrients come out of those than without fertilizing than our extensive roofs. So just focusing on my stormwater design roofs, we have the same compost in all of them. So that's not a controlling, so we have the same organic source at the same level in all the tables. So as an experimental design factor, the source of nutrients should be the same in all of those tables. So then it comes down to the materials that we're using as the substrates and the permeable reactive barrier as to whether those are making a difference. So we've isolated the substrate materials and the PRB materials as the design element. What are we using for the PRBs? We have zeolite, and we have 2 different sources of biochar. One is a wood-based biochar, and they're not technically biochars. They are char products, but of pyrolysis, but they are char products, but they're not technically biochars. So we have a wood-based char and an oat hull-based char. I wish I could say that I had done 2 years of column studies to specifically choose these materials because they had the potential for working. Zeolite, I chose zeolite because we used zeolite in our green roofs in New Zealand, and zeolite had beneficial uses for plant growth, and zeolite has high cation exchange capacity. We know zeolite holds on macronutrients and is good for plant growth. It's used in all Gulf turf greens in New Zealand because of its nutrient support. So that's why zeolite. The chars were because the stormwater world seems to be going crazy over biochar. but nobody knows how it works, why it works. We're starting to understand, but very, very beginning of it. Why did I choose those two biochars? Because those two biochars were the only ones that were the right particle size distribution and that anyone knew anything about that could interpret for stormwater. So chars everywhere. Everyone, I heard the laugh. I appreciate the laugh. I do that laugh. Everybody's crazy about biochar. But the biochar suppliers, the vast majority of biochar suppliers that I have spoken to don't understand what we're doing and aren't interested. And I found a couple that are interested. Your particle size distribution is a major factor. Most of the biochars I've come across that are commercially available are dust, and that's just going to and they just wash right out of my systems. So honestly, this is a really long answer. The biochars that I'm using are because they were available at the right particle size distribution, and the supplier, it's the same supplier, it's biological carbon from, they're in Oregon. He was willing to engage in a conversation about stormwater and already knew something about it. So it's not this great study design where I knew these materials or I had an idea. It's what's available to me and what can I make use of that's available to me. Very roundabout way of answering your question. Did I answer it? Okay.
Yes.
Do you have a recommendation for organic content as a percent?
For green roofs? Yeah. Yes, under 10% by volume. So we did a study back in Auckland of green roof and bioretention media, and we varied the organic content between 0 and 20% amongst different aggregates. So different pumice varieties for green roof blends, different sand varieties for bioretention media. And we measured plant available water, and we measured all these agronomic methods. And in this under 20% of organic content had no measurable, not a significant measurable impact on the amount of water holding, on the amount of plant available water. What was significant was the aggregate. We had, namely, for the bioretention media, we had a marine sand and we had a pumice-based sand. And the pumice-based media, and so now these are bioretention media, the pumice-based bioretention media held much, much more water than the marine sand because it's a rock that holds water in its pores. So even just a sand specification, all bioretention media has a sand specification, but the type of sand matters. And it matters a lot more than how much organic content you use. Everybody, the conventional thought is that you need the organic matter to hold water, and that's what holds water in these systems. At these low additions, that's not the case. It's the aggregate that has a bigger effect. What I've seen in growing a lot of green roofs in 2 different climates now is when you choose the right plants that are adapted to those growing conditions. So whoever is specifying the plants needs to understand the growing conditions. And the growing conditions are created because this is a stormwater control as a first priority. And there's a really wide range of plants that are available to us, even under these really limiting growing conditions. So you can have a low compost addition, have a very, very viable green roof, have an excellent stormwater control, and minimize that potential for leaching nutrients.
So do we have a question from online? No? Okay, good. So we'll finish the talk right here, and then we'll rearrange everything for a panel discussion, which will start in 5 minutes. Let's thank Elizabeth.
Thank you all very much.
Welcome back. My name is Andy Erickson. I will be moderating the panel discussion. To start, I will introduce our panelists and give them a moment to express their reaction or relation to this topic of performance metrics. And then we will open it up to questions from you, the audience, both in person and online. If you have questions online, please type those in the Q&A chat and we will voice them here to get them answered. But to start, I will introduce our panelists. First, on the far left side, my right, is Ed Matthiesen, who's a principal engineer at Wenck Associates. So Ed, what is your relation to this topic of modernizing performance metrics?
Thank you, Andy. I'm the engineer for 2 watersheds in the metro area, Shingle Creek and Coon Creek watersheds. And it's a topic I'd say we like to do this, but for cost reasons, it always falls off the chart for us. That we pretty much go back to the standards, and I'd have to say 1950, the 1964 one really isn't that long ago. Let's get that out there. That we design and build and put stuff in as we think is probably the best thing to do and the most cost effective, and the monitoring comes later. And so now we're starting to do some monitoring because a lot of this work, we've essentially proved proof of concept, I think. And we take some limited studies and we start applying that in the field because we've got pollutants that are coming online with E. coli and other harmful organics. So we want to get something out there that's passive and kind of the best technology available, but it could only be studied for 3 to 5 years, a couple of studies when we started putting it out in the field. So we start doing proof of concept designs or studies in the field, but our metrics are really limited, very, very low.
Thanks, Ed. I'll introduce our next panelist, who's Tim Sundby. He is a Water Resources Program Analyst at Carver County Watershed Management Organization. Tim, what's your reaction or relation to this topic?
I think the big one, and Ed's talked about it too, and Elizabeth, has been that testing. That's been the one part where it's really hard to get kind of performance data out of a lot of these BMPs that we've been putting in, kind of relying on literature and what Andy does here at this lab, kind of some of those reduction numbers, but at the same time, we're putting in, different areas, where I work at, it's a lot of clay soils, and we don't know if the percent that we give for volume reduction is actually working. So being in a WMO, we have that unique situation where we are the policy maker, and then we also have the ability to go out and monitor this. And having a manager that's really pushing that, it's been nice that we can actually get out there and do a lot of this testing over some period of time. So that's our next step right now, is actually getting into that testing and seeing what we're putting in is actually matching our design plates that we're giving to engineers and developers. So I think that's a big one for us.
Great, thanks, Tim. Our next panelist is Ben Janke, who's a research associate here at the University of Minnesota, affiliated with St. Anthony Falls Lab and other departments and other projects. So Ben, what is your relation and reaction to this topic of performance metrics?
Sure. So, of course, my perspective is a little more academic than our other panelists, which means that I'm not used to working in the framework of, say, TMDL development or compliance with permits and things like that. So I feel like, with the exception of the work that you and Dr. Gulliver do on assessment of BMPs and performance, I'm kind of working one step back from that and working on developing a better understanding of how urban watersheds work, understanding nutrient sources and transport, and focusing more on the watershed management side of things. And that's just kind of the nature of the work I do. So, where I think often in the academic world, we're kind of criticized fairly for not taking that translation step to take our research and turn it into something like performance metrics or something, or some other metric that might be useful. So maybe not load reduction, but maybe it's, attenuation of flows or duration, flow duration, something like that. So this has been it was very interesting to hear Elizabeth talk, and I'm interested to hear more about what our other panelists say, but have been doing a lot of work focused more on kind of the source reduction and management opportunities that we get from understanding some of the details of the data that we collect.
Great, thank you, Ben. And we just had Elizabeth's relation to this topic. So now I'll open up to questions. I'm going to start us off with kind of a general question, kind of set the framework and the ground. What I'd like to hear from the panelists, from your experience. So in Minnesota, we're very familiar with this percent reduction, percent removal, right? of BMPs. So we assign some number to a type of BMP. So maybe not even a specific BMP in a context, but just a general number for all BMPs of that type. I'd like to know kind of where have we seen that fall short, right? Where has that really held us back or limited us? We've seen, you know, it's hard to go beyond that sometimes in our projects, but where are we really kind of holding ourselves back on that?
I'll take a whack at this. We hope it works. As engineer for a couple of watershed organizations, we review a lot of grading and drainage and erosion control plans that have to meet both state standards and the particular watershed standards. And the watershed standards are often changed to reflect the TMDLs, total maximum daily load plans. So we get a grading plan in from a developer. We don't have enough information to tell them that what you're proposing for the 60 or 80% TSS reduction is actually going to meet our TMDL load. We think we're close, we hope we're close, but we're not going to probably know for another 30 years as we do more testing in our watershed. Another problem we have is sometimes the devices they have, we're not really sure that that is even close to what the performance standards are. So the good side is, I'll shout out the SAFL baffle, has some good performance data that we can rely on pretty well. There's a competitor coming out of Iowa, Preserver, that we're a lot less sure of the results on because the testing protocols aren't the same. So on the design side, knowing what you're working with the products is really all over the map. There's really not much for standardization in that. So that's one thing we'd like to have. And then going into the watershed itself, having, as we progress with TMDLs and knowing where in the watershed we need better performance, that will evolve. But as we said on the earlier statement, the monitoring money just isn't really there for watershed organizations. But I think we're getting closer. So I'm going to have other thoughts on that I'll kind of interject later.
Any other responses?
Yeah, I can jump into some of these different BMPs that are more innovative. Just trying to get a % reduction out there is tough to do. I know Carver County, we've been doing a lot with reuse, and to come around on how do you quantify some of that sometimes. We went from when we were doing the designs on that, it was just the amount that you would be irrigating. Didn't really look at the source or how much water is coming into a pond or a storage area. So we really had to revamp just on our design metrics, let alone how do we monitor that and say, yes, we are meeting what we said, you know, what we permitted. So I think some of the newer BMPs, that's kind of the big area where trying to get a % reduction kind of falls short every now and then.
Okay, so I'm gonna now talk about why I think % reductions are not a good metric in and of itself, or are not good as a standalone metric in and of itself. And I'm thinking about the receiving water. So a % reduction, just the math of a % reduction, how it's calculated, is in minus out divided by in. It's a change from a starting point. You're measuring a change from a starting point. And stormwater is so highly variable, right? Your concentrations or even your mass loads from storm to storm at the same site can vary by orders of magnitude. So measuring a % change from that starting point changes drastically from storm to storm, but is also misleading if you're starting with a low stormwater concentration and having an effect. You can still have a clean effluent, but a low % removal. So this is just a story of math, right? 10 minus 6 divided by 10 is not the same of 2 minus 1 divided by 2, right? Those are very different % removals. But if I'm talking about 6, I just picked numbers. I should never pick numbers out of the blue sky. If I've got, let's say 60, because that's a better, like if we're talking about TSS, if I've started at 100 milligrams per liter of TSS and I'm reducing only down to 60 milligrams per liter of TSS, or 20, that gives 10 to 20 gives me 100 to 20 gives me an 80% removal, but I've still got 20 milligrams per liter of TSS discharging off my site. If I started at 20 and went down to 10 milligrams per liter, I've only got a 50% reduction, but I've got water that's twice as clean. And what does the receiving environment care about? The receiving environment cares about how clean is the water that's actually discharging in, not what happened on the land. So that's just one piece of the percent removal metric issue, but I think that we need where the percent, so one of my partial response to your answer, but I will stop after this, is that a percent removal metric does not enable us, does not really think about how clean is the water that's actually entering the receiving environment. And it's a receiving environment that we're trying to work on.
Right, and kind of what I hear through all of this too is that hint at variability, right? One storm, one site, 1 year, right? Even if we're doing testing and monitoring, it can be very hard to establish even a percent reduction for a particular technology or a site. So that variability there is huge, and especially if you're not taking the context and thinking about what is the in, what is the effluent, and we're trying to boil it all down to one number, right? That's kind of the power of the flow duration curve or percent exceedance or some of these other methodologies, is you get to look at all of the data. And I agree, that's where I see this kind of falling short. We're trying to get one number and boil it down and simplify it so much that we really miss the whole picture, right? So do we have any questions from the audience for our panelists? Please.
So I can see now how our seminars are building off each other in terms of technology, in terms of monitoring. I think my question is for Elizabeth, but maybe everybody. To consider alternative performance metrics, we need data in. Are we missing something in the monitoring stages to be collecting the right information for us to be looking at alternative performance metrics?
That's a great question. I think the answer, that off the top of my head, my answer is we're missing capturing the variability. The vast majority of funding that goes at least towards academic research is for a 1 year, 2 year monitoring period. And your ability to capture performance over this wide range of conditions is really, really limited. I love that your WMO is getting into monitoring, and you have the capability to do that those long-term studies. So I think that's where the experimental design, that's the first place that the experimental design falls short. And so that's a funding issue. It's not a technical issue.
Sure, I could add to that. I think first I would just put in a plug for a lot of the watershed districts and management organizations here in Minnesota that are doing a lot of data collection. They are also very happy to share their data with us academics, to do the best we can to put together bigger data sets. So for people like me who get really excited about this and can look at spatial patterns or that kind of thing. But it is tough doing our own work, where we have 1 year of funding or maybe a year and a half, and we have to collect a whole season and then try to say all this stuff about 1 season of data collection. In a current project, we are kind of working on ponds specifically and trying to figure out if there are some other pieces of data that could be collected easily along with the standard monitoring data. So if we had maybe a time series of water level in the pond, something simple like that, or just putting out thermistors to get temperature information to know whether the pond is stratified or not and how often it's mixing, if that could give us some information about how the ponds are performing and coming up with some, I think the idea would be if we come up with say a reduction, a percent removal that varies with season or varies with the hydrology of the pond to make it more accurate. I think that would be, so that I guess that temperature data or maybe wind speed or water level, that's an example of some additional data that potentially could be collected, I think, relatively straightforward fashion.
I think the one thing I do want to say is that a lot of our design plates, we have to have something up front. So we make it as easy as possible. So when we go to a developer, it's cost effective for them to put it in the ground. So we rely a lot on literature values, and it is does take that time where, you know, Ed was saying, we put it in and it's there. It's really tough to get that monitoring up front. So that's what we're doing. We're trying to catch it on the back end after it's already in, and we're going through rules updates every 10 years or 5 years. And at that point, that's when we say, is it working as we said it would? So that's kind of, I know it's a little bit backwards on trying to get that monitoring data up front. And unfortunately, just making sure that development still moves forward, the monitoring becomes on at the back end for our site specific monitoring. And I think that that is a challenge, because we can't put that on a developer and say, hey, you're planning on putting X in the ground. Will it work? Prove it to us now in this specific site. And that's really tough to do. So we're kind of on that back end. And I got to be honest, our monitoring is pretty rudimentary. We're just putting a level logger, seeing how much water is going in and out, and take the concentration so we can get mass. And that's what's kind of the low-hanging fruit for us.
As a practitioner, I'm doing design work for these same BMPs. And there's two components that I come at. One is the manufactured treatment devices, which I think because you go to a laboratory like SAFL or some other university or third-party testing organization, should be a requirement that they go through some particle size distribution, influent testing that has at least sufficient amount of samples so that as a practitioner, I can pick something off of their data that is uniformly tested so I can compare product to product. So that's one element, the manufactured treatment devices. The other one are constructed in place BMPs. And those are all over the map because every site's different. So that's where the watershed organizations comes in, the owners, and possibly the state, to help out of, say, long-term sampling, because everyone's going to have a different watershed area use type, even change of use over the lifetime of the device or whatever system was installed. So as a practitioner, I'd like to then go into something like our state stormwater manual that has enough data in there to say, okay, I can tell the client that if we pick this, we've got a reasonable chance that this is going to last 15 years, and our annual operation maintenance and taking capital costs, so we can back it into year zero. We need to put aside this type of money in order to make this work, and we've got a reasonable expectation we're going to get this type of performance out of it. So I think there is those two components for what I use for treatment systems. One is what you can go off the catalogs, pick something out. That should be, I think, a manufacturer's requirement to hit some standards. The other one kind of falls back to the owners, that we're getting this data and then we're sharing it with enough other people so that the practice moves ahead. We just know more.
Can I make one more comment? Okay, so still thinking about John's question, and there's another piece, I think, to the puzzle which fits in more, which adds to the ability to use the performance assessment, not just to choose the right technology, but to be able to predict for your clients whether over the long term things are going to work. And that is, I think that we need to work harder on designing our monitoring setups to understand flow mechanisms and flow processes and pollutant removal processes. So in versus out gives us the snapshot of performance. But what do you use to design for your client? You use a model, right? You might use SWIM, you might use, I don't know, there are a whole lot of different models out there, but you're using a model to predict performance for your client or for the regulatory agency to guarantee some sort of chance of success. Well, those models, particularly for green infrastructure systems, are not calibrated. Their accuracy is not proven. And now I've played around with a bunch of them, and I know there's a lot of work to be done there to improve the accuracy. But to improve the accuracy, we need the data to support development or redevelopment of that model. And that data is about the flow mechanisms and the pollutant removal, or the pollutant fate and transport through a system. So monitoring just in and out is going to give us a piece of information, but if we want to improve the models, we need to be measuring flow pathways, how the water moves through the system. So in my bioretention planters and my rain gardens, I have them set up with lots of internal sensors. We've got TDRs to measure soil moisture. We've got tensiometers in there to try to track the path of the flow through the system. And that's going to hopefully help us develop the right algorithms for a model to then predict flow through the system. So I think there's a lot more internal looks and internal measurements that we need when we're doing our BMP monitoring design. And then there's a whole other part of that conversation about the accuracy of the sensors that we're using. But yeah, I think we have to look inside the black box more so we can develop those models to better help the designers.
Other questions from the audience? We have one from online. Let's take that one quick.
The question regarding the different soil textures that you might recommend for a green roof or a different type of practice. Have soil textures, including small amounts of silts and clays, been included into the engineered media analysis or recommended mixes? And would that assist with the plant health and slow filtration or flow delivery? And can early quality control issues be overcome? So lots to unpack there.
I had most of the same question just recently, and it was from a plant person. And it's a really good question. So it's my understanding that the silt and clay particles are really, really beneficial for plant growth for a number of different reasons. And that is, but their presence is kind of in direct odds with managing flow hydrology. So being able to pass enough water through a bioretention system during the course of a storm event, and not clogging up your media. My short answer is no, I don't use silt or clay in any of the media that I have been testing. But part of that is because the design guidance that we have, there's a chicken and egg thing, right? Part of the design guidance we have says, do not pond water on a rooftop, or water needs, your bioretention cell needs to drain within 2 to 24 hours. Some of that's for mosquito breeding, or sorry, sometimes it's 2 to 3 days. That's for mosquito breeding. So where do you start? If I started from, I'm designing a system for great plant health, then I might have included silt and clay. But I'm starting from a stormwater control and a design manual that someone came up with somewhere that said this is the starting point, and it doesn't include silt and clay. So how's that for a non-answer? Was there another part of that question? I think I got it.
I guess, anybody want to add anything to that? Okay, let's take another question here from the audience.
I want to thank you for showing the after the green roof systems that were involved there, because I think that's a big factor in how we deal with the storm water. And if we can treat it before it goes into the storm cell through a sand media, for example, I used to get credits for the green roofs here in Minneapolis when I were putting them in, and I told them, I said, I'd rather get a credit for this sump that we put over here that is all grass, that's actually a lot easier to deal with than having one 20 stories high or even 3 stories high. And yet I'm accomplishing the same thing. I'm filtering it through there. One of the questions was about clays and silts. I built sports fields for years, and the best fields that I had built were basically if they had a little bit of soil in them. I don't want the silts at all, because those are going to clog up the systems. They run through the sand medias. The clays, if you can keep the clay percentage down low enough so that it actually matches with the amount of surface space you got on the sands, then they're going to give you the nutrient holding capacities that you want for the systems. So I really appreciate the downward things, because we've got plenty of materials and sands that we can use in storm ponds, even if it's dredge sand. I've used dredge sands in various sports fields. There's no problem with it at all. It's clean washed sand. Particle size makes a difference as to how deep the profile has to be, but that's about it. So.
Any comments?
Yep. your comments made me remember the other part of the question, which is there any hope for quality control? Sort of. What we is my answer to that. So in particular for green roofs, you know, they're the last choice of most designers because they're the most expensive of all the BMPs that are typically available to us. So when we were figuring out how to design and build green roofs in Auckland, I was going from the standpoint of what can I use that's already available and not have to change anything, you know, because I don't want to add a specialty product or screening or anything that'll increase the cost. And the quality control of the materials we got was poor. And so rather than saying, oh, this is a poor, rather than saying, oh, this is a poor material, instead we took a step back and said, okay, this isn't what we thought it was going to be based on its, you know, written description. Let me put that aside. Let me go and just do an objective assessment of what these products actually are from my own interpretation. I hope that makes sense. And what happened was I found a pile that had enough small particles. So it was a Fassman-Beck that was supposed to be 4 to 10 millimeters, right? That was the particle size distribution, but there was enough what we called in contamination of small particles, much smaller sand-sized particles in that mixture that gave me the small particles I needed for supporting plant life, but it wasn't in the spec. So the contamination and the quality control worked in our favor once we understood what that product actually was, and I could work within those existing product lines. So the quality control may not always be there, but we took the time to understand what the industry was providing. So we had to take a step back and could make it work.
But the the Golf Course Association has done all of that work on a specification. So if you look at that, or the Sports Turf Association specs, they're both great because they keep the minimum particle sizes out.
Sure, and in North Carolina, their bioretention media specs a ball field mix because that's very consistent. Those are more expensive products. I was able to use a concrete spec, which is dirt cheap.
Other questions from the audience? Mike, go ahead.
Well, excuse me, I'm one of those regulators, design guidance people, so I have relatively thick skin, so it's okay. But as someone who does develop guidance and lives in the regulatory world to some extent, is there a way we can kind of flip this a little bit? Because we have always obviously focused on the BMP. How does the BMP perform? But is there some other way we should be approaching it in our regulations and in our guidance that would the systems thinking you were talking about before?
Go ahead, please.
I think you could make it part of the grant requirements. There's a lot of money still available in the Clean Water Fund. I think one of the requirements would be, what is your monitoring plan for the life of your project? And that'd be a requirement that you have to share it with the state. So lately the requirement's been, you've got to guarantee this product for, well, I forget what it is now. I know it's going to be like 30 years. For 20 years. It's a long time. Essentially, I told my wife I'm not retiring for a long, long time. So don't get your hopes up. But if you can get that programmed in with the watersheds, my clients I have, we can just factor that in as a cost. And assuming that we're going to get 4 to 6 samples per year, so over a number of years, you get a statistically relevant sample size. And out of that, then having, what are your design parameters? What's the watershed size? What's the use? Just about all of us have some hydraulic model. That would be also included with it. And over the period of life of that product or your BMP, how has that changed over time? So you can measure it. Most of our systems don't necessarily go into just an urban area that stays static forever. It's always undergoing some change, and a lot of our products are going into areas that are right on the edge of development, so that watershed's changing over time too. So trying to take that factor into consideration for the designer and for the watersheds that have to respond to their TMDLs and their permitting loads would be worthwhile. So on the front end, I think if you could just put it in as a state requirement that when you're handing out grant money, this is a requirement you have to do, then we can get it programmed in and just make it part of the project cost and amortize that over the life of the project.
Other ideas?
I think that we need to do some thinking about what are some simple metrics. So to keep the cost of monitoring down, if we're just trying to figure out, does it work, does it not work, or has the performance deteriorated because of lack of maintenance or a condition in the watershed has changed? There's got to be something easier to measure than what we are measuring now. Like the data that we're collecting now, pretty resource intensive to collect. And I know I haven't thought that much about what's a really simple assessment, a basic assessment that actually is related to performance. It's not necessarily, oh, we've got 2 inches of sediment built up, this thing obviously isn't working anymore. That's not the way it works. We know with permeable pavement that part of your parking lot part of the surface can get clogged up, but the rest of the parking lot can still manage all the flows. So just because a piece of it's clogged doesn't mean the whole system has failed. But I think that we should spend some time thinking or playing around with different measurements that are actually meaningful for performance from a long-term, that's going to inform long-term O&M. Because there's got to be a yes or no kind of answer that's a lot easier to do than the way we collect data now. Because what we do now is really, takes a lot of work. It's super fun, but it takes a lot of work.
I think another example to address your question, Mike, is kind of looking at source control or source reduction. And I know a project that you're familiar with is trying to put street sweeping into a crediting framework. And that's work that Jacques Finley and Sarah Hobby and Larry Baker are working on currently, trying to basically make a BMP equivalent, I think, out of street sweeping and the phosphorus removal associated with that. And I think that's a good example of getting away from a lot of focus on BMP or end of pipe type treatment and looking at, it's a little bit harder to look at the effectiveness of something like that. It requires a pretty intensive study to quantify the reductions associated with street sweeping, for example, or maybe we do pet waste cleanup in the spring or something like that. They can, they're kind of a little bit different sorts of approaches that are more at just keeping the nutrients, keeping the pollutants out of the stormwater system in the first place.
So let me pose this question. Thinking about, we've talked about BMPs and Elizabeth talked about, broader scale, right? Ecosystems and larger targets than just BMP, individual BMP performance. And I'm sure we've all seen, there seems to be some kind of disconnect between performance we see in individual BMPs throughout the landscape and the ultimate water quality we see in a watershed, right? Even if we measure and monitor all of our BMPs and we get numbers, we still don't get a direct relationship with the resulting water quality in our ecosystem or in our target water bodies. So thinking about maybe other metrics or even other monitoring, other things we could measure. What are some of these things that maybe we could measure on a broader scale, bigger system, that can maybe get us closer to our targets, tying what we're trying to do on the landscape with what our actual targets in our water bodies and our ecosystems are. So for example, industrial wastewater, they have effluent standards, right? You measure the concentration. It's very easy metric relatively to measure, right? It's at a point, you can do it over time, you can determine how often you exceed that value. Maybe we could do that in stormwater. That's been proposed, right? On the national scale and on local scales. What other things could we maybe do that looks more broader than an individual BMP performance?
Like I can start off, just looking at our monitoring network, we try to have a station. We've had, there's probably 9 stream sites across our county that have been in for at least 20, 25 years. And it's really tough to quantify the impact that BMPs have, whether it's in an urban setting or a rural setting. We're trying to quantify for TMDLs to say, yes, we are doing all these BMPs, whether it's on a field, edge of field, or in the middle of a city. And we can see the numbers are going up. We've done a lot of stuff, but it's still really tough to quantify what that change is. So I don't know what that next step is, just because there is so much that can happen to that drop of rain after it's treated from that site to the watershed. And, you know, we always talk about, you know, you put it in a pond and that water that's discharging or out of a tile, it's really clean, clear water, typically. I should say devoid of sediment, but right away that water wants to pick up sediment. So you start seeing these gullies happening because this tile is starting to pick up, after it leaves, it picks up more sediment. So it's kind of, that's the challenge that we have as a WMO is how do we answer that question are we making a difference? So I kind of want to hear what other people want to say on that.
I think it would be interesting to go back to some of the sites that were monitored a long time ago, and see. So if, you know, maybe this is a little bit more oriented on the maintenance. Does maintenance matter, and are we having an impact? Part of the question. But we've got studies from 10 years ago, from 15 years ago. Those sites are still there. Probably people have forgotten about them, right? So wouldn't that be a great opportunity to go back and monitor those to see has anything changed? Has the performance changed? Or in an ideal scenario, there would be a receiving stream assessment from 10 years ago and go back to those same spots and see if anything is different, and if so, why? So revisiting, we've got enough time in, I think that it's time to revisit some of our old sites. And whether that's on a watershed scale or a site scale, you could ask a lot of really good questions instead of always coming up with a new spot and a new technology.
Some of the watersheds I work with have sampling now for 40 years. And we've got the same site. So at some parameters, we can see that we're actually having an effect. So a phosphorus load, TSS load, decreasing. Chloride load, absolutely no change. Bacterial load, still off the map. But we're seeing some positive responses with our lake bodies that some are coming off the impaired waters list within an urban area, which I thought is, in my career, I probably would never see, but that's occurring. So we're having some effect as we keep adding more projects in and BMPs in. So I think, fortunately, I work in an urban area. Working in a rural area is a lot harder, I think. For the funding's not there, you don't have the flow already collected in a pipe, so much diffuse flow. So at least in an urban area, we can do this, and we've had the financial resources to do the monitoring. So both on the stream side and the lake side. I think we're seeing a better result in our lakes than we are in on the stream. Plus now, at one point, if we can get enough of the inflow for phosphorus and TSS down for inflow into lakes, then we can hit the internal load and have an alum treatment. It seems to be the most cost-effective way. That response then generates an immediate, hey, you guys are doing great response from the public. Keep it up. So that allows us to do more projects too. So doing the monitoring on the lake and the stream side, I haven't got a better solution to do that. And for cost effective, the citizen assisted monitoring program with SecuDepth is relatively inexpensive, gives us water clarity data. But that's just measuring water clarity and to try to tease out what all affects that and the things we're having. Takes a whole team to figure that out, and I don't know if we have the right answer yet.
And I think a related question to that, and something that I've seen and heard people bring up before, is how much of your watershed needs to be treated by a BMP before you actually see an effect downstream. And there are success stories, of course, of lakes that have been taken off of TMDLs, but by and large, we aren't seeing much of an improvement for all the money that's gone into projects. And so maybe it's just we don't have enough of the watershed being treated, or there just aren't enough projects in, or maybe they aren't working, as intended or as designed. I don't know what the answer is, but I've gotten this question before, and I don't really know how to answer it. But I've seen some work where people have tried to do paired watershed studies and figured out, well, we have maybe a 10% increase, or 10% lower total phosphorus concentration in stormwater coming from this watershed because it has 30% more BMPs or something. I think maybe just what I'm hearing too here is that we're sitting on a lot of data, between Metropolitan Council and MPCA and the watershed districts and the cities. There's a lot of data here. And I know some people have tried to tackle this, and say, how are we doing in terms of improvement in water quality, or trying to understand the changes in time. Is it just a land use change? Some of the improvement is just now that land has all been developed and the grass is growing and the trees are bigger, we're seeing a reduction in TSS and phosphorus just because there's more vegetation growing and it isn't being developed or something like that. But if we could take that effect out and look at the BMPs that were placed in the watershed over time, could we kind of use a time as substitution for to assess performance over time, I guess, to see how the BMPs are doing. I think that would be interesting.
I think you bring up a really good point about we're sitting on a lot of data. And I mean, being trained as a civil engineer, I'm not trained in big data, right? Or dealing with big data sets. And this is where I think is another set of scientists that we need to reach out to. And those are the data science folks or the software engineers. So I've been doing this with software engineers at Stevens who are, so my systems are instrumented to all get out, right? I've got, I lost track of how many sensors collecting data on 1 minute intervals when it rains. And it's a lot of data to manage. And if I had to use the techniques that I've always used, which is Excel and doing it by hand, you'd never get through it all. But integrating with data science folks and software engineers are helping. There was a big learning curve, but automate a lot of that raw data processing, and then you can just focus your energy on teasing out the information you want. And now you can just play with the data and look at so many different things because the raw data processing has become so easy because I brought in someone who knows how to do that. I think it's not okay to think we can do it all ourselves anymore.
Yeah, you don't want to try that. I've done
it. Lessons learned, right?
Yeah.
Other questions from the audience, please.
So I was interested in Dr. Elizabeth's statement that we should really be we should really be regulating phosphate, orthophosphate instead of total phosphorus. I know that there are times when and conditions when particulate phosphorus can become orthophosphorus and vice versa. And so I'm wondering what the panel thinks about the idea of regulating orthophosphorus instead of total phosphorus. I don't know, so I'm just wondering.
On the watershed side, it's a very good idea. I think we've gotten pretty good at dealing with soluble phosphorus. And then what we're seeing, and it's also your work too, what we're seeing in the watershed organizations is we're converting that soluble phosphorus in an anoxic condition to dissolved phosphorus. And now we're starting to release that into the downstream waterways. So I like the idea that I saw with a green roof of that phosphorus capturing filter. So now we're starting to put in some devices to see what's the most cost-effective means to deal with the dissolved phosphorus, since that's so readily uptaken by the plants. So I think regulating to it's probably worth some good thought.
Can I add a caveat to my presentation? I want to point out, I think I unfairly poked a finger at green roofs, but I didn't give the whole story. So we should be concerned if our BMP designs create sources rather than sinks, right? So that's the general concern with nutrients, from whether it's a bioretention system or a green roof system. But with a green roof system, very specifically, the number one thing is the vast majority of storms are almost completely retained. So you're up to your 1-inch storm event. If you've designed your green roof well, you get no runoff at all. Which also means that the only storms you can capture to analyze those water quality samples are big storms where your system's not performing well, no matter what. So those data that I showed are event by event, are event-based, not a long-term mass load. And because there are so few storms that generate runoff. And to capture that variability, I'm working on a long-term data set to try to use a statistical approach to develop a long-term mass load analysis. And that's my very long way of saying it's absolutely possible that the long-term mass balance does work in a green roof's favor, but we don't have that data yet. In the meantime, we know when and if we get discharge, we should design that system to think about the orthophosphate and the nitrogen coming out of the system. Or maybe not nitrogen. Nitrogen's actually, I didn't talk about this at all. Turns out it's atmospheric. It's not from the green roof. That was my caveat while I had the opening.
I think we are at that point where I think moving to orthophosphate and kind of have that as a regulation, I think we're at a point of understanding that I think would be it'll be easier to do than what it would have been maybe 10, 15 years ago. And understanding that it will be that added cost of an extra filter or an extra BMP, I think that's going to be the challenge rolling it forward. Whenever you change any kind of policy or standard, you're always going to have that pushback. And we still, after 20 years of standards in Carver County, we still get that conversation right away when a developer comes in and goes, why do you have that 1-inch water quality standard? Why is that there? And that's after 20 years of around the metro area of having that standard. So I think that's going to be the big challenge moving forward on that. It's just having the buy-in on the policy with everybody. That'll be big.
But then, is the counter argument to that, well, you still want to spend, $50,000 or $100,000 on a system that doesn't make a difference just because it ticks a regulatory box that doesn't have the effect it's supposed to have?
Correct. It's kind of, I guess that it's a good counterpoint. It's always, the developer and their pushback never looks at the end result of stormwater. Stormwater is the last thing they look at, and they have a budget of probably a tenth of a percent of the overall project they dedicate to stormwater. So they look at the box that as a policy or as an ordinance, they just want to check it off as quickly and easily and cheaply as possible. So once we add that extra policy, they're going to look at the bottom line. It's like, I'm not going to make as much money, so why am I doing it? And I think that comes back to us as an educator and say, yes, that does make a big difference. You become a great neighbor of passing your water downstream. And that's the education part where sometimes we lack as a policy writer. So it kind of really comes back to education. And I know John likes to hear that with education, but that is a big part of what we do. We need to educate those developers and say, yes, you add an extra 5,000 to your bottom line, but the water quality coming off your site is so much better. And for the people that'll be living there or working there, their potentially tax dollars are going to be less because it's not going to problems downstream.
I can see how there's also a piece of this conversation or a part of this conversation that's about potentially opening up the regulator to a challenge from the public or someone else saying, well, we have all these systems in place that were designed to do something else and we spent a lot of money on that, and now you're telling me it doesn't work or it's not the right thing to do. That's a bit of a conundrum. And I don't think, I could see the challenge being posed that way, to which I would respond, what we've been doing has been using the best available information. And now we just have so much more information that it's time to move on, right? Nobody uses a dial-up phone anymore. We didn't have those tools, and now we do.
And I think that even ties back to these metrics, right? If we talk about percent removal, that can be very hard to explain to people, and they can see the news that there's all the variability, and this study said it doesn't work, that study said it does work. We really don't even know what we're talking about is some of the arguments we get, right? So getting into things where we can talk about uncertainty, and I've heard even using the word uncertainty with the public is not wise, because that just tells them we don't know what we're talking about, right? It's about variability. And so if we use some of these other techniques and educate through that, then we can get that message out. So other questions from the audience?
Can I throw another question in? Is anybody talking in Elizabeth in your systems? Are you working the microbiome activity at all? Okay, so you're not measuring things because of the biopopulation that's in it or anything like that?
No, but that's, I would say largely because that's not my expertise, and it's a matter of finding those people.
Well, the thing I was thinking about is when we don't contaminate things like our waterways, for example, Lake Erie, when I grew up, Lake Erie was never going to be a good system for hundreds of years. Lake Erie was not going to be a fishery for hundreds of years, but we stopped putting crap into Lake Erie, and now it's a fishery again. So Mother Nature does a better job than we do in many instances,
Well, isn't that kind of the point of green infrastructure?
Yeah.
I mean, I look at green infrastructure as engineering nature, right? We're trying to manipulate it to work a little bit better, a little bit harder in a more confined space.
Maybe you just need to think like a microbiologist.
Maybe I need to start thinking like a microbiologist. And honestly, that's part of the reason I'm excited for the new opportunity in Southern California with the Southern California Coastal Water Research Project. It's an agency full of scientists. There's a whole microbiology department. There's an ecohydrology department. There's a biogeochemistry, I think. I mean, it's all these ologists, right, that know what those effects are and can help me. I'm really excited to work with them to try to pull more of those pieces into the picture.
Other questions? So what I would like to do now is I'm actually going to wrap up. I'm going to give my panelists another chance to respond. Now this is looking at forward. What can we do with this information as practitioners? How do we manage our water resources better? So what's maybe one thing you'd recommend to our audience here in general that we can take away from this and maybe make changes in what we're doing every day, hopefully to get to a better place in the near future? So Ed, maybe we'll start with you down at that side.
Go back to my earlier comment of putting in a requirement when we have grant money. Watersheds I work with also distribute grant money, that we make it a monitoring requirement as part of that dispersion of money.
That's great.
I think trying to make it as simple, not too simple, but as simpler for trying to monitor the key areas. So when we're looking at this 10, 15 years down the road, or right now, we have 2-3 metrics that we can really hone in and say this is the main drivers. I think that would be a big step moving forward.
Yeah, I think these are both great ideas, incorporating long-term monitoring, but maybe simplifying it in some way to get it down into the most relevant or most useful parameters. I think that would be great. And then maybe the last step, I'll just say this again, but getting all the data together so that we could get data scientists, maybe not engineers, working on this, but organizing and analyzing these data to figure out if there are some bigger patterns we can see, something that pops out like, oh, we really just need to know how much the water level changes within the first 24 hours of a storm in a stormwater pond or something like that. If it's just something, or if it's more related to the soils of the region or something, or the land use in the last 10 years, something like that pops out, that becomes really useful, I think. And that would be really cool.
Oh, I think I've had a lot of chance to say what I think should be done, but for me, I think my immediate response is to try to work with more scientists who understand the receiving impacts and think about how I can back that up into BMP design and what kind of data I need to collect to link all that up.
Right. So it sounds like we need to talk more. We need to get information out. We need to share. We need to work together as a group. So with that, I will thank you all for joining us for today's Minnesota Stormwater Seminar Series. Please help me give a round of applause to our panelists and our speaker. Thank you.